Okay, so hi and welcome to this presentation on the continuum hypothesis. I will try to explain, kind of give a whole overview of the topic and explain how it was proved to be independent of the CFC axioms. We will go over two very relevant proofs, um, some of which parts are quite complex, but hopefully I'll provide some good high-level understanding and some intuition regarding what these proofs are trying to do. So yeah, let's begin. So, the continuum hypothesis. The continuum hypothesis states that there exists no set whose cardinality is strictly between the countable and the uncountable. So more formally, can be expressed as follows. This statement says that the CH states that exists no set S uh, whose cardinality is strictly greater than the cardinality of the natural numbers, which we call countable, and the strictly less than the cardinality of the power set of the natural numbers. So a bit of history to begin with. The continuum hypothesis was proposed by German mathematician Georg Cantor in 1878, and despite his extensive work, he could not prove or disprove the continuum hypothesis, and it remained one of the most intriguing open questions in set theory. And David Hilbert, one of the most influential mathematicians of the late 19th and early 20th centuries, included this problem as the first of his famous 23 problems, presented in the year 1900 at the International Congress of Mathematics in Paris. So now finally in 1940, Australian mathematician Kurt Gödel finally made some progress, and he showed that the continuum hypothesis is consistent with the CFC axioms of set theory. So this means basically that it cannot be proven to be false from within the CFC as it is consistent with them. So Gödel's work overall marked a shift in mathematical thinking, from seeking definitive answers to understanding the limitations of formal systems. Also around this time, he proved his famous incompleteness theorem a couple of years earlier. So how exactly did he prove this? So before we can delve straight into the proof, we need to define some terms first. So we define the generalized continuum hypothesis as follows. This says that Aleph sub alpha plus 1 is equal to 2 to the Aleph sub alpha. Basically, this is a pretty natural extension from the continuum hypothesis. Suppose we define the cardinality of the naturals to be, which is the first infinite cardinality, to be Aleph sub 0, and let's say that we define the cardinality of the power set of the naturals to be Aleph sub 1. We can keep going and keep on defining discrete cardinalities by applying the power set. We can have the power set of the naturals to be Aleph sub 2. So basically what the generalized continuum hypothesis is saying is that there is no set whose cardinality sits anywhere in between these discrete cardinalities. So basically it's saying that the amount of cardinalities, there's a countable amount of cardinalities. Okay, so next definition, given a set X, we define the set def X as follows, and we can see the definition on screen. So basically the notation def X refers to the definable elements of a set X. Specifically, it's the set of elements Y in X that satisfy a certain property, and where this property is described by a first order formula, which we call phi. A first order formula, phi, is an expression in first order logic, and this is the type of logic that uses quantifiers that range over individual elements rather than sets or functions. This includes everything from variables, logical connectives, so like and, or, not, quantifiers like for all and there exists, and binary relationships such as like belongs to in a set. And then finally, last term we'll define is transfinite recursion. This is a method used in set theory to define functions on well-ordered sets, particularly on ordinal numbers, which extend beyond the finites. And this process allows for the construction of objects or the definition of functions step by step over an ordered set that includes infinitely many elements. And this is relevant because we'll see how Gödel used this in his proof. So now delving into his proof, how did he prove it? So first of all, he built what we call the constructible universe L. So he defined this universe L using a concept called constructibility, and the universe L is built up in stages, which are indexed by ordinals, and we can define it formally by transfinite induction as follows. We have that L0 is the empty set, and then the inductive step is that L sub alpha plus 1 is defined as the definable elements, as we've seen before, of L sub alpha. And then if lambda is a limit ordinal, which is just defined to be an ordinal that has no successor, so kind of an infinite ordinal, if you will, then L sub lambda would be the union over all the alphas less than lambda of L of alpha. And two more remarks about the constructible universe L, which are important, is that L is an inner model of V. V is represents the class of all sets. It's also known as the universe of set theory in the context of CFC, and it is the broadest possible collection of sets that can be talked about in CFC. So in more formal terms, V is the cumulative hierarchy of all sets that can be constructed, starting from the empty set and going upwards through all possible applications of the power set operation, unions, and subsets definable by first order properties. It's very similar to L. The universe L is defined very similarly using the constructive hierarchy, where each level is constructed from the previous ones by considering all these sets that are definable using first order formula. And the key difference is that L contains fewer sets than V at each level, and this is because it contains only the definable elements from the previous stage and not all possible sets. And then one final remark about L which is very important for our proof, is that L is a model of CFC. What this means is that the axioms of CFC hold in this constructible universe L. So the axiom of regularity, existentiality, axiom of the empty sets, axiom of pairing, axiom of union, axiom of infinity, axiom of separation, replacement, axiom of power sets, axiom of choice. Hopefully I'm not forgetting any, but basically all the axioms of CFC hold in L. And this is very important because if L were not a model of CFC, then Gödel's construction would not work to prove the consistency of the continuum hypothesis within CFC, because it would be if it weren't a model of CFC, it would be trying to prove a property about a system using an argument that does not apply to that axiomatic system. So the proof would not be valid. So now delving into Gödel's proof more directly, this can seem a bit complex and maybe abstract at times. So I'll try to unpack it step by step, and also I'll use the analogies of a skyscraper and on a library and a huge library to kind of visualize what is going on. So yeah, let's get into it. So the proof begins by saying let S be a subset of L alpha and let T be any constructible subset of S. Then there exists some beta with T in L sub beta plus 1. such that T is defined as follows, and T equals the set of all x in L beta, such that x is contained in S, and phi of x and zi. So so let's begin unpacking this. So we start with a set S, and we'll say that it lives on the floors of this mathematical skyscraper, which is L, specifically on the floor numbered alpha. And T is a particular group of elements we picked out of S, and have been put together following this building rules, let's say, which just means that it's constructible, right? Then we say that we can find a higher floor, namely beta plus 1, where T fits perfectly. And every element of T is an element of floor beta, chosen by specific criteria, which is phi, using elements from the same floor as tools, or we can say references. So in simpler terms, T is a set which we can fully describe with this recipe, which is phi on floor beta, and all of its elements are part of floor beta plus 1. Okay, so then moving on, by the downward Lowenheim-Skolin theorem and the Mostowski collapse, we obtain a transitive set K containing L sub alpha and sharing the same first order theory as L sub beta. So here we're using kind of a, we can say, a mathematical magnifying glass, which is this downward Lowenheim-Skolin theorem, and a smart collapsing technique, which is the Mostowski collapse. And we managed to create a mini model, which we call K, that looks like a smaller version of the floor beta, but contains the entirety of floor alpha. And it's also a transitive set, which means that if a group of objects belongs to it, then every object that those objects contain also belongs to it. So basically nothing is left hanging outside. Then the proof states that the transitive set K will have the same cardinality as L sub alpha, and hence can be identified with L sub gamma for some gamma having the same cardinal as alpha. So basically it's saying that despite K looking smaller, like a smaller model of beta, it actually has the same number of elements as L sub alpha, so the same cardinality. So then given the above, T is effectively in floor L sub gamma plus 1. And then it follows that all constructible subsets of S have ranks with at most the cardinal K as the rank of S. So this is an interesting observation. This is saying that all the groups we can build using the elements of S fall within a certain range, or here we call it rank, which we've named kappa. And kappa is sort of a label that tells us where S sits in this hierarchy of our mathematical skyscraper. And this leads to L intersects P of S serving as the power set of S within L. So by intersecting the universe, this universe, constructible universe L, with the power set of S, which is like gathering all possible groups of elements from S, we find that they all live on or before the floor delta in our skyscraper. And so finally, assuming that S has a cardinality cardinal K, the power set of S in this universe L has cardinality exactly the successor of kappa. Then L has the so then assuming that S has cardinal kappa, then the power set of S in L has cardinal exactly the successor of kappa, which perfectly aligns with the generalized continuum hypothesis relativized to our universe L. So basically this proves that the generalized continuum hypothesis holds in this constructible universe L. So also I would like to explore. It's similar, but maybe in kind of simpler terms. Um, the same proof but with a library analogy. Um, so we're talking about in our previous proof we're talking about a special set S which sits on a specific level of our structured universe, which we call L, the constructible universe. And we can think of L as this giant library with many shelves, where each shelf or level contains sets that are built step by step from simpler shelves below. So now let's say we pick a particular set of books, which we call T, from one of these shelves. And this set T isn't just any random collection, but it's a carefully chosen collection from a specific set of rules, which was denoted by phi, and it used a list of ingredients which are elements from that same shelf. Then we proceed to use this kind of magical lens, which is provided by this pair of mathematical tools, the Lowenheim-Skolem theorem and the Mostowski collapse, to focus on S and its special subset T. And this lens, in a sense, has the power to preserve the order of our library, and it allows us to view T as if it were on the next shelf up. And so by doing this, we find something very interesting, which is that no matter how large our original set S is, all the sets we can construct from it neatly fits on the shelves up to a certain point, which is the point we called kappa. And here's the twist, that if we try to collect all possible combinations of books from our set S into a mega collection, which is just the power set, it perfectly fills just one shelf above kappa in our library L. So what does this mean about our understanding of the library L? So it shows that this structured library universe has a very specific organization, which is one that supports the generalized continuum hypothesis, which is a statement, in this case, about the sizes of the shelves in our library relative to L. So yeah, basically this shows that L supports the generalized continuum hypothesis, so therefore also the continuum hypothesis. And we've said already that L is a model of CFC, so this shows that CFC that the continuous hypothesis is consistent with the CFC axioms. So moving on, so we can then prove that it's true, right? Then, but no, we in fact in 1963, American mathematician Paul Cohen demonstrated that the continuum hypothesis cannot be in fact shown to be true using the CFC axioms. We cannot use the same method that Gödel used to prove that that CFC plus not CH is also consistent. So instead, Cohen had to invent a new method, which is called forcing, for his demonstration. And this demonstration also earned him the prestigious Fields Medal in 1966, which is the only one ever awarded in logic thus far. So again, before we start, we need some definitions. In this case, for the second proof, we'll need quite a few, and some lemmas as well before we can delve into the actual proof. Just a warning before we start. Cohen's proof is quite complex and has a lot of subtleties, and also a lot of the notation he introduced. So it's not some standard notation. So in some cases, I'll omit the details and I'll make more emphasis in what the significance of the definition or a lemma is with regards to the bigger goal of demonstrating not CH is consistent with CFC. So yeah, without further ado, let's get into the definitions. So definition number one, we say that a forcing notion is a partial order capital P, and we have the notation greater than or equals, containing a smallest element 0 sub big P, and its elements are called conditions. So just a remark here, a partial order is a binary relation, which we see the symbol there, over a set capital P that is reflexive, which means that every element is comparable to itself. It's also antisymmetric, so no two different elements precede each other, and it's transitive. So if an element precedes a second, which precedes a third, then the first element also precedes the third. And a smallest element in the context of forcing means that that it's the weakest condition, or the one that makes the less amount of commitment in the forcing notion. And okay, as it says in the definition, the elements of a set P are referred to as conditions. So definition number 2, a subset G of a forcing notion capital P is an ideal if it's not empty. So this simply means that the subset G contains at least one condition from the forcing notion capital P. Because I mean, an empty set would not be useful for forcing, because you would need some conditions to work with. It has to be directed. So if P and Q are in G, then there exists R in G, such that R is in this context greater than P and Q. Simply means that the condition is stronger than both P and Q. So yeah, and also it is downward closed. So if P is a member of G and P is a stricter condition than Q, then Q is also in G. So basically this property ensures that G contains all conditions that are less constraining than any of its elements. And then moving on to definition number 3, a set D, which is a subset of the forcing notion, is dense if and only if, for any P in the forcing notion, there is a Q in D extending P. So let's unpack this definition. So D is, as you can see, a subset of the partially ordered set P, which is the set of all conditions in the forcing notion. And here the term dense refers to a particular property of D within the order P. It means that for every condition small p in capital P, you can find a condition Q in D which is stronger than P. So in this case, extending P means that Q is at least as restrictive as P or more, which in the context of forcing we note as greater than or equals. So in the process of forcing, a dense subset is significant because it ensures that no matter what condition you start with, you can always find a stronger condition, which is one with more information restrictions in this dense subset D. Okay, so moving on to definition 4, it says that let capital P be a forcing notion and D be an index family of dense sets. An ideal G is D-generic if it intersects all the dense sets. And we also say that G is P-generic over M when it is generic for all the P dense sets in M. Here the part we care mostly about is something being P-generic over M. So here M typically denotes a model in set theory. In our case, it can be CFC. And G is P-generic over our model M if within the model M, G intersects every dense subset of our forcing notion P that exists in M. And this ensures that the filter G captures all the quote-unquote necessary conditions that the model M thinks are dense, allowing G to force this new model. So with all the things we have defined so far, we can move to our first lemma, which we're not going to prove. It states that Let P be a forcing notion, D a countable collection of dense sets, and P a condition. There exists a D generic ideal G. The most important part here is, so as mentioned previously, the term ideal in the context of forcing should be considered as a filter. So a D-generic filter G is a collection of conditions from our forcing notion P that meets every dense set in the family D. So what this is saying, this means that for every dense set D sub n, there is at least one condition from G in D sub n. So moving on to definition number 5, we get introduced to the p-name. We say that a p-name is a set of the form sigma and small p. So enforcing a p-name, or simply it's called sometimes a name, is an object that is used to refer to elements of the set being constructed in the forcing extension. So it is a way to describe elements and sets in the larger model, which is called the extension, as opposed to the ground model, which is the base model we're starting with. So a p-name is composed of ordered pairs, sigma and p, where sigma is itself a p-name and small p is a condition from the forcing notion large P. So the point of p-names is to allow us to talk about objects in the larger universe, so the extension, before actually constructing that universe. They provide a way to describe how the new sets added by forcing will be built up layer by layer from the conditions in the forcing notion. Moving on to definition number 6, it says again, let P be a forcing notion, G an ideal, or as we mentioned, generic filter, and tau a p-name. The evaluation of tau is the set tau of G, the ideal or generic filter. So without delving into details, so in simpler terms, tau of G is the set you get when you quote unquote apply the generic filter G to tau. And this evaluation process gives us kind of quote unquote the real objects in this new forced universe from the potential objects that were described by p-names in the ground model. And moving on to definition number 7, let P again be a forcing notion, and giving a formula phi, a condition small p, and p names tau 0 to tau n, we say that P forces sigma evaluated the p names, and that's the notation the stick with the perpendicular one to write the forces or entails sometimes. If and only if for all p generic ideals G, such that small p is in G, we have that M evaluated at G entails again our formula phi, and the p names are evaluated with the generic filter. So without delving into too much detail on the specifics, basically this definition of forcing is a technical way of specifying how a condition in the forcing notion can guarantee the truth of a particular statement in any model that is extended by a filter containing that condition. And this is important in forcing, as it provides a precise method for showing how certain statements can be made true in the extended model. So finally, our last two theorems, which are important in our proof. First one is the truth lemma, and I'm not gonna delve into the specific of the notations, but essentially the truth lemma is essentially saying that a statement about the evaluated p names is true in the force model if and only if there is some condition in the generic filter which, according to the ground model, ensures the truth of that statement in the extension. And finally, theorem number 4, um, which is arguably the most important, specifically, especially in terms of the intuition behind forcing, which is the main theorem of forcing. Um, Basically, it's what this theorem is doing. It's relating the truth of our the truth statements of our ground model and our extended model. So this theorem is stating that a condition small p in the forcing notion, um, capital P, forces a particular formula phi involving p names to be true in the extended model if and only if from the ground model M the condition P is seen to force phi to be true in any generic extension containing P. So it relates the truths in the ground model and the extended model. So before moving on to the main proof, I wrote down kind of my own summary of the main ideas of forcing, which kind of maybe could have gotten lost in all these formal definitions and lemmas which are required for the formal proof. So I would like you to stick with the following ideas. So the ground model is our starting point, which is a universe of sets where certain mathematical facts are true. So in this case, we can take a ground model to be the CFC axioms. And then to create an extension, we introduce these generic filters or ideas. And these are collections of information that help us decide how to add new sets to the ground model. And you can think of generic filter as a carefully selected recipe that preserves the original truth in our ground model while expanding it. And so the nice thing is that when we apply a generic filter to the ground model, we ensure that nothing we knew to be true before is changed, so all the original truths remain intact. However, we now have new sets that we can use to make new statements true. So it gives us more power, basically. It allows us to explore what could happen if we had more sets than we originally started with. Okay, so moving on to the main proof, in which the aim is to force not CH in the extension of our ground model of CFC. Which is evaluated using the G or generic. So the basic idea is to tackle the problem. The problem is to add Aleph sub 2 many different elements of 2 to the n to our ground model M, which is CFC. And consequently, using the truth lemma, we will have that the cardinality of 2 to the n is greater than or equals to Aleph sub 2, which is greater than Aleph sub 1 in M evaluated using the generic G, which we know is a model of CFC since G is generic, so all the truths of CFC are preserved. It complies with all the axioms of CFC. Hence, we refute CH. Below we see more detail how this is done, but I'm not gonna delve into the subtleties. Also, something that is not mentioned here, but we also have to take care for the formal proof is something called cardinal collapse, which basically means that Aleph sub 2, or actually any cardinal seen from the perspective of our extended model, might not equal the same cardinal as seen from the perspective of our ground model of CFCs. That is not trivial. But there's actually another theorem which proves that, at least in this case, I'm not sure in the general case, they actually are the same. So it successfully completes the proof. But so in summary, the approach taken here is that it uses Cohen's forcing, which is a specific type of forcing using partial functions from the naturals to 0 or 1, to add a whole lot of new subsets to n, to the natural numbers, to ensure that the cardinality of the reals in this extended model is at least Aleph sub 2, thus refuting the continuum hypothesis in this model, which is also a model of CFC, so it actually serves to refute the continuum hypothesis in CFC. So yeah, the model M evaluated at G is shown to be a model of CFC because G is a generic filter, and by the truth lemma, if it follows that the statements about the cardinality of the continuum that are forced by the conditions in G also hold in our ground model. So yeah, we were able to force not CH, and after all of this, I think for this complex topic, some analogies are sometimes useful to grasp the main concepts. So I really liked, I found it somewhere and I kind of developed it, I took it and expanded it a bit. This house analogy of what was going on, and the kind of, it's not exact, but it kind of helps to kind of grasp intuitively what's going on here. So if we imagine the CFC axioms as a kind of this nice house in the center, we can picture Gödel's constructive universe as the architect's blueprint, for instance, which is like a carefully detailed and precise plan where every part has a specific place and role, so kind of mirroring the way the constructible universe L contains sets that are strictly definable and necessary, and this, in this framework, it was easier for Gödel to demonstrate the consistency of CH. And on the other hand, we have Cohen's forcing extensions, which can be thought kind of as a process of expansion and customization of this house. Just as you might add an extension, like I don't know, a conservatory, or choose a new color theme. Cohen's method adds new sets to the universe that were not previously considered, without altering, of course, the original structure of the house. So this doesn't change the foundational integrity of the house, but it expands the living space, let's say, allowing for more possibilities and configurations, kind of aching the way forcing expands the set theoretical universe to include these new subsets of the naturals, thus demonstrating that additional axioms, like for instance not CH, are consistent with CFC. So, what does this mean? So, put together these two results, the works of Gödel and Cohen, prove that the continuum hypothesis is independent of the CFC axiomatic system, because we've shown models in which CFC is consistent with CH, and models in which not CH, models of CFC in which not CH is consistent. So therefore, it's independent of the CFC axioms. This is similar to how Euclid's fifth postulate was independent from the first four. Therefore, one can assume either CFC plus CH or CFC plus not CH, and get two different yet consistent models of set theory. So what happened since? Just a few developments since Cohen's proof. So from the 1970 onwards, following Cohen's work, the technique of forcing became a central tool in set theory, leading to deeper understanding of the structure of the set theoretic universe and the nature of infinity. And it's primarily used also in proving independence results in similar spirit to the continuum hypothesis. Also, there were other concepts developed, like large cardinals and determinacy in the 80s and 90s. Research in large cardinal axioms and determinacy theories during these decades provided new insights into the potential structure of sets and the limitations of ordinary set theory. And these eras explore concepts that extend beyond the standard CFC framework and have implications for the CH. One notable mathematician who worked a lot on this is Hugh Wooden, who's a notable figure who made significant contributions to the understanding of the continuum hypothesis, Wooden proposed that the universe of sets is significantly larger than it was previously believed, and introduced a new set of axioms like the omega conjecture, which suggests that under this axiomatic system the CH is false. And his work has sparked renewed interest and debate over the truth of the continuum hypothesis in a broader set theoretic context. And in the 2010s, Wooden also developed the concept of ultimate L, which is a model of set theory that attempts to unify much of the set theoretic practice under a single coherent framework. And this model predicts the failure, also again, of the continuum hypothesis, providing a new perspective on the problem. So yeah, this is the end. Thanks a lot for listening to this presentation. Hopefully you left with at least a better understanding of the continuum hypothesis and the strategies employed to prove its independence from CFC. And yeah, that's it. Thank you.